Hi guys, welcome back to my channel. Today we are continuing our investigation into how ancient structures may preserve warnings, not just myths. In the last Myth Mechanics episode, we explored ancient Egypt's symbolic language and architectural precision and the mechanics of sound. That foundation helps set the stage for what comes next. Structures like the pyramids may hold more than cultural meaning. These monuments seem designed to persist across the ages, pointing to events much larger than a single civilization. Their placement, alignment, and materials raise questions that standard historical timelines tend to brush aside. For instance, the orientation of the Great Pyramid aligns almost perfectly with true north, using techniques that shouldn't have existed according to conventional models. This level of engineering invites a different kind of interpretation, one that treats the pyramids as a message built to last. One angle worth exploring views the pyramids as mechanical timepieces. They resemble complex timekeeping systems with internal chambers and shafts aligned to celestial events. These alignments suggest a dual purpose, religious or ceremonial meaning paired with functional knowledge. And indeed we see ancient Egyptians closely tied their rituals to celestial events, aligning them with agricultural cycles, royal legitimization, and religious festivals. The Nile's rise and fall, along with celestial phenomena like the rising of Sirius, influence their calendar, agricultural practices, and religious observations. Rituals often involve daily offerings to deities in temples, ceremonies celebrating the new year, and other festivals, agricultural designs that reflected astronomical alignments. So we see that their structure acts like a clock that marks cycles in the sky, and potentially cycles in the earth itself. If builders were tracking something rhythmic and destructive, the monument could function as a durable signal. In this view, the pyramid becomes a warning system encoded in stone. Its survival through multiple cataclysms may reflect that goal. Geophysical clues point in a similar direction. Patterns of erosion around the Sphinx and the Giza Plateau support the idea of an older origin, possibly tied to periods of intense climate change, that shifts the timeline and opens the door to broader interpretations. If ancient builders experienced or anticipated major environmental upheavals, it would make sense to create permanent structures that communicate across time. The pyramid's resilience suggests its purpose includes stability through instability. As a result, we can begin to think of these monuments less as tombs and more as anchors. They remain standing when everything else shifts, possibly even the crust beneath our feet. This brings us to the core question. What kind of shift would be important enough to mark in stone? The pole shift theory proposes that Earth's outer shell periodically slides over its core, rearranging continents and triggering global upheaval. Structures like the pyramids may also slip atop key stress points or nodes, helping track or mitigate these movements. The idea may sound bold, but it fits with the concept of rhythm, something Earth itself seems to express through extinction cycles, glacial patterns, and geomagnetic changes. If ancient cultures knew this, they may have encoded the timing in architecture. We'll explore this further through physics, solar influences, and historical records, starting with a look at the science behind crustal displacement. From there, the pieces start to connect. Crustal displacement theory centers on a simple but impactful idea. The Earth's outer shell can move independently of the inner layers. This concept was popularized by Charles Hapgood, who suggested that the planet's crust occasionally shifts due to uneven weight distribution, causing large-scale reorientation. In a 1955 letter, Albert Einstein himself supported Hapgood's exploration, writing that the idea was original, of great simplicity, and if continues to prove itself of great importance to everything that's related to the history of the Earth's surface. That said, Einstein did not claim it was proven science. The theory gained attention in the mid-20th century before drifting to the edges of academic circles. While plate tectonics eventually became the dominant model, crustal displacement still raises questions that hold value. These include the causes of abrupt climate change and the rapid repositioning of land masses. Modern research offers new angles for looking at some of Hapgood's claims. Studies of ice cores and glacial shifts in both hemispheres suggest that major transitions in climate may happen faster than once thought. For example, In 2014, Zhang demonstrated that abrupt glacial changes were likely controlled by ice sheet collapses, not slow and steady processes. Fossils found in polar regions also point to sudden environmental shifts rather than long-term evolution. These findings help frame crustal displacement as a plausible mechanism in certain periods of Earth's history. While Hapgood's specific model lacks modern support, the idea of rapid geographic change has returned through different scientific doors. In particular, new tectonic models simulate large-scale reconfigurations over relatively short geological windows. This keeps the conversation open. Government and institutional research further support the need to re-examine sudden shifts. NOAA and NASA both collect and publish data on Earth's magnetic history, revealing periodic fluctuations in pole position and magnetic strength. These records include events like the Lachamps excursion, which marked a major dip in the magnetic field strength around 42,000 years ago. Although this event was a magnetic excursion rather than a physical displacement, its global effects underscored how sensitive Earth systems can be to internal changes. Paleomagnetic studies track movement in magnetic orientation preserved in rocks, giving a timeline for past changes. Some of these align with known mass extinction events and major sea level shifts. This correlation invites further research into whether these movements come with crustal consequences. At the very least, the data show Earth's stability has a pattern of interruption. These interruptions help form the backbone of a pole shift discussion today. Crustal displacement offers one framework for understanding the physical side of the pattern, especially when combined with magnetic and solar data. Modern science continues to explore rapid geophysical changes through more refined tools, including computer modeling, satellite monitoring, and sediment analysis, all of which provide a clear picture of the planet's past. These tools expand our view without fully discarding earlier theories. The result is a hybrid understanding where older ideas get tested with new evidence. This growing conversation about rapid Earth changes set the stage for one of the most controversial entries in the pole shift discussion, the Adam and Eve story. While much of the modern research into geophysical shift relies on measurable data and cautious modeling, there remains a parallel thread of interest in more dramatic scenarios, especially within government archives. Few examples capture that crossover between fringe theory and institutional curiosity better than the presence of Chan Thomas's book in the CIA's declassified library. In 2013, a redacted version of the Adam and Eve story by Chan Thomas appeared in the CIA's online reading room, sparking renewed curiosity about the document. Originally published in the 1960s, the book outlines a series of rapid events. While Thomas's writing includes some speculative and theological material, the fact that it ended up in the CIA's archives raises questions. At the very least, it signals institutional interest in extreme geophysical scenarios. The archived version includes technical illustrations and narrative focused on rapid crustal movement. The Earth's crust is displaced in around 1/4 of a day, Thomas writes, accompanied by global earthquakes, massive floods, and sudden windstorms. These descriptions mask the structure of a crustal displacement model, even if the framing reads like science fiction. Chan Thomas included detailed timelines describing ancient cataclysms, suggesting that past civilizations were erased by rapid Earth movements. He wrote of winds that reached up to 1,000 miles per hour, and oceans leaving their basins to sweep across continents. While these specifics lack scientific backing, the broader structure matches known records of sudden climate change. For example, the Younger Dryas period shows evidence of rapid global cooling, possibly caused by atmospheric disruption. The USGS has published sediment core data indicating abrupt freshwater pulses and flood events around the same era. Thomas may have been drawing on fragmented evidence, weaving it into a more sensational framework, but the foundation aligns loosely with real events. The CIA's decision to archive the document suggests it held relevance as a thought experiment or reference. The CIA's decision to archive the document suggests that it does hold reference as some kind of evidence to this. Institutional interest in rare disasters often centers on risk management. Government bodies routinely model low-probability, high-impact scenarios, especially those that affect critical infrastructure. In this light, the Adam and Eve story functions as one entry among many that propose disruptive Earth changes. Whether or not it was used actively, its preservation suggests that it held value in contextualizing global risk. All civilizations are wiped out, Thomas claims. with only a few survivors in isolated pockets. That idea resonates with flood myths from multiple cultures, of which echo themes of fire, darkness, and sudden collapse. These shared memories may reflect distant ancestral experiences of rapid climate events. When cross-referenced with data from organizations like NOAA and the USGS, the timing becomes even more interesting. Periods of strong geomagnetic activity, extinction pulses, and sea level changes often appear grouped around the same windows that Thomas described. Though the specifics differ, the pattern is consistent. Large, sudden environmental disruptions occur on a cyclical basis. This overlap helps position the Adam and Eve story as more than a curiosity. It becomes a cultural document reflecting possible ancestral memory shaped by geological events. And while Chan Thomas's delivery may feel dramatic, the broader picture connects to data-backed questions about Earth's long-term rhythms. That opens the door to examining how angular momentum and instability might contribute, which brings us next to the Dzhanibekov effect. The Dzhanibekov effect, sometimes called the tennis racket theorem, describes how a rotating object with uneven mass distribution can unexpectedly flip during motion. This behavior was first observed in space by none other than Russian cosmonaut Vladimir Dzhanibekov in 1985, when a wing nut began rotating steadily and then reversed its axis mid-spin. The effect results from having three principal axes, with the middle one being unstable under rotation. In simple terms, when the mass distribution isn't uniform and an object rotates around its intermediate axis, it can suddenly change orientation. On Earth, this principle has been used to study the motion of satellites and free-floating tools. The same math applies to any rigid body in free rotation, including theoretical models of the Earth's crust. The flip is not due to an external force alone, it's baked into the rotational dynamics. This behavior has inspired speculation about how Earth's outer crust might respond under certain conditions. The idea proposes that if enough stress builds up through mass redistribution, solar influence, or internal shifts, the crust could reach an unstable threshold. At that point, it could pivot or lurch, behaving similarly to how the wing nut flipped in space. There's a widely circulated video demonstration that I will link below that makes this visual readily apparent. The flip doesn't require constant pressure, but happens once internal balance reaches a specific tipping point. While Earth is not technically a free-floating object, the principle offers a model for understanding instability and rotation. This gives researchers a potential analog for how crustal displacement might occur. Earth, because of its lumpy mass distribution and geoid shape, contains the right conditions for this effect in theory. However, under normal circumstances, Earth's stable orbit, internal dynamics, and gravitational environment prevent this type of flip from happening. Essentially, the Sun acts as an anchor to our Earth, so it's not technically free-floating. But a micronova event could temporarily override these stabilizing factors. This type of event involves a sudden burst of plasma and photons from the Sun, capable of stripping Earth's atmosphere and overwhelming its magnetic field. The resulting shockwave could induce heating within the planet, particularly on the side facing the blast. This uneven heating would cause rapid expansion on one side of Earth's crust, building pressure along fault lines and weakening the crust's grip on the mantle. If that pressure reached a tipping point, the crust could slip or even rotate independently for a short time. If this disruption lasts long enough, Earth's liquid core would allow for differential rotation between the crust and deeper layers. The combination of asymmetric heating, weakened structural integrity, and torque from solar plasma could destabilize the Earth's rotation just enough to trigger a Dzhanibekov-style flip. In this scenario, the event would likely unfold in three dramatic stages. First, there would be a sudden lateral shift of continents causing catastrophic earthquakes and flooding. Next, a period of chaotic rotation would follow, with skies moving unpredictably and the Sun appearing in strange positions. Finally, Earth would stabilize again, potentially with a new axial orientation, an outcome echoed in ancient myths, frozen animal remains, and maps showing different historic shorelines. The model suggests that an abrupt movement could happen without violating physical laws. The math behind this possibility comes down to torque, angular momentum, and time. Torque is the force that causes an object to rotate, and in this case, it would come from the asymmetric push of a micronova's plasma blast. The formula is simple. Torque equals the change in angular momentum divided by the time over which that change happens. And it's on screen. Maybe here. I don't know. It's on screen. Enormous mass requires an equally enormous force. But if enough energy is applied suddenly and unevenly, even a stable rotation can destabilize. A short duration but high intensity event like a micronova could deliver the necessary torque in minutes or hours, temporarily overcoming Earth's internal stabilizers and allowing the crust to slip or flip onto its unstable rotational axis. The Dzhanibekov effect does not predict such behavior in Earth's crust directly, but it allows for a new way of thinking about this rotation, balance, and sudden reorientation. It provides a reference point for the kind of instability that might trigger large-scale shifts. In this context, it's less about proving a model and more about seeing what kinds of motion are physically permitted. This connection becomes even more relevant when we consider historical patterns of mass extinction and geomagnetic instability. If Earth's crust were to shift suddenly, the results would include earthquakes, climate disruption, ocean displacement, all of which match mythic records and fossil data. The Dzhanibekov effect offers us a physics-based mechanism to support these outcomes without invoking fantasy. It brings the conversation into the realm of mechanical possibility, giving the broader theory a solid conceptual base. But now that we've established a model for how this movement can occur, the next question becomes why it would happen at regular intervals. And so that brings us to the sun. Specifically, the idea that solar events, like a micronova, would act as a trigger. The sun plays a much larger role in Earth's long-term stability than daily weather patterns would suggest. Solar energy drives climate systems, but solar activity also influences Earth's magnetic field and atmospheric chemistry. In recent years, researchers have explored how large solar events like coronal mass ejections and solar micronovae might act as trigger for wider changes. Solar forcing can lead to disruptions in the geomagnetic field, which helps shield the planet from cosmic radiation. When that field weakens, radiation levels at the surface rise, impacting both DNA integrity and atmospheric dynamics. These shifts ripple through ecosystems and may contribute to widespread environmental change. Patterns in solar cycles appear to overlap with known extinction windows. Several peer-reviewed studies have suggested links between solar behavior and biodiversity loss, especially when paired with geomagnetic fluctuations. One example is the Champs excursion. A 2021 study in Science by Cooper found that this magnetic weakening likely influenced solar conditions, correlating with two major ecological and cultural changes. They wrote, the temporary breakdown of Earth's magnetic shield during the Champs event could explain many major transformations. These include megafaunal extinction, cave art booms, and migrations. While correlation, of course, does not guarantee causation, the timing supports the idea that solar shifts play a major role in terrestrial change. These cycles are regular enough to study and irregular enough to surprise us. Sediment records and ice cores help ground these theories in physical data. Layers of beryllium-10 and carbon-14 produced by cosmic rays spike during periods of weakened magnetic shielding. These markers show up in polar ice samples and deep-sea cores aligning with known solar minima and geomagnetic excursions. In several cases, these spikes coincide with signs of cooling, fire, or flood events in the geological record. When these magnetic fields weakens and solar activity is high, more cosmic radiation reaches the Earth's surface. This affects climate patterns, mutagenesis rates, and possibly tectonic activity depending on the scale. The patterns suggest a feedback loop between solar cycles, magnetic shielding, and Earth's environmental responses. Together, they point toward cyclical disruptions that align with the larger pole shift framework. If solar activity can disturb Earth's protective systems, then it can also act as a timer for crustal instability. This connects the dots between solar physics and geophysical movement, setting the stage for models that include both external forcing and internal tipping points. The micronova theory, though still under review, offers one way to explain bursts of solar energy that exceed the usual cycle. Events of this kind would raise global temperatures, weaken the magnetosphere, and redistribute atmospheric mass, all things that could trigger displacement in a sensitive system. From fossil layers to magnetic anomalies, the evidence forms a repeating structure, and that structure includes mythic memory, fossil shifts, and climate collapses tied to solar timelines. As we move on to the final section, we return to the pyramids with a new lens. The pyramids continue to stand as one of the most persistent signals from the ancient world. Their alignment to cardinal directions is so precise that it still prompts questions from architects and surveyors today. The Great Pyramid of Giza is aligned within a fraction of a degree to true north, a feat that suggests long-term observation and intention. Some researchers have noted that these alignments may shift in relation to Earth's axial orientation, hinting at a possible awareness of pole movement. The idea of using stone monuments as fixed reference points becomes even more compelling when viewed in the context of geological cycles. Erosion patterns around the Sphinx and other structures on the Giza Plateau also suggest exposure to intense and ancient water flow. These clues imply that the builders may have been responding to events that shaped both landscape and memory. Star maps carved into stone, temple layouts mimicking constellations, and monuments oriented towards celestial events all point toward timekeeping. The pyramid complex has been interpreted by some as a three-dimensional calendar, grounded in both astronomy and geography. If the ancients observed patterns of catastrophe triggered by solar cycles or geophysical shifts, they may have designed their monuments to track recurrence. And this is something that we see throughout the ancient world. We even see cave art down in the southwestern United States that can be interpreted as solar events happening that these people would have wanted to record because it was such a cataclysmic event that they have to tell the next generation and preserve its memory. To speak to the future, build with what the earth cannot move, might be the underlying logic of this. These structures function like mechanical anchors in a system of time that includes stars, floods, fire, and art. Myths passed down across continents reinforce this idea. Stories of global floods, sudden darkness, and fiery skies appear in cultures from Mesopotamia, like we've covered, to Mesoamerica. These stories often describe world-ending events followed by rebirth, survival through select individuals, and knowledge preserved in symbolic form. Many of these myths line up with the paleoclimate data that points to rapid environmental change. The Younger Dryas, the 8.2 kiloteer event, and the Lachamps excursion all leave traces that align with these themes. Whether the memory comes through oral tradition or stone carving, the underlying structure repeats. It reflects a pattern of periodic destruction that seems to sit at the foundation of many ancient belief systems. The pattern, embedded in both geology and culture, suggests observation rather than just imagination. The pyramid, in this light, is a message encoded in geometry, geology, and sky. It stands as both a monument and a marker, a signal from those who lived through cycles we are still trying to understand. When these monuments are mapped against magnetic anomalies, crustal movement zones, and extinction timelines, the connections start to build. The pyramid may record data through its structure, aligning to past pole positions and forecasting future ones. The stories that surround it, of gods in the sky, floods from the heavens, and rebirth through disaster, begin to read like records, not metaphor. Together, structure and story preserve a timeline of Earth's instability, written in both stone and story. The question now is whether we're willing to read it. The pattern that runs through all of this is quiet but consistent. From geological records to mythic stories, the message points us in one direction. Something happens here on Earth, and it happens on a cycle. The pyramids may hold a key to that timeline. When we read them as monuments, we get one story. When we read them as markers aligned to stars, tuned to magnetic shifts, and set with precision, then we get another. If the ancients tried to warn us, it was not superstition, it was memory. That memory might be fragmented, but it's carried in stone, story, and sediment. Thinking of these ancient monuments as warnings rather than just tombs or religious structures opens a different conversation about what knowledge survives and how. These structures remain when almost everything else fades. That endurance could be part of the message. Build strong, point to the sky, and align with Earth's true axis. If shifts come with the sun or built up with tension in the crust, then knowing the cycle might matter more than understanding the trigger. From Hapgood's early ideas to solar cycle data, the pieces begin to fit when placed into a pattern. The consistency of extinction timelines and magnetic events backs the concept without needing to stretch the science. These monuments then can stand as both anchors and clues. So where does that leave us? Maybe somewhere between curiosity and caution. The goal isn't to sound an alarm, but to pay attention. If our ancestors built messages into their monuments, stories, and myths, reading them might help us understand the pace and rhythm of our own age. The past doesn't predict the future, but it does give us a map of what's possible. Anyway, that is all for today. Hope you enjoyed it. Please don't forget to like and subscribe like the winners that you are, and I will see you next time. Bye!